7, I think. Okay. Yeah, so what we are trying to prove is that there is this intimate connection between the modular condition and the modular automorphism group. And this is the theorem we were trying to prove, that if we have this von Neumann algebra R, and you have omega, a faithful normal state, then there is a unique one parameter automorphism group, one parameter group meaning strongly continuous one parameter automorphism group. So then there is a unique one parameter automorphism group satisfying the modular condition. So automorphism group of R. So group of automorphisms of R. And I should actually add star automorphisms. Yeah. That satisfies the modular condition relative to R. Relative to omega, sorry, modular condition relative to omega. And the general strategy of the proof was that, first of all, without loss of generality, you can go, this is a faithful normal state, so you can have a faithful GNS representation. And then you get a cyclic and separating vector out of it, the vector we have been denoting by a U. And then what we did first was figure out that alpha T of A was, in fact, you could figure out a corresponding UT. In order to show that this was one parameter, the definition, but to prove that UT was in fact a strongly continuous group, you just had to see that you have to use the modular condition. So used the modular condition. So modular condition would say that so omega, so alpha T A B U dot U. So for any AB in R, so this is actually a continuous function in T. So we use that fact. In fact, it's a continuous and bounded function in T. We use that fact to establish that this UT was in fact strongly continuous one parameter group of unitaries. Use the modular condition here to show UT is a strongly continuous one parameter group of unitaries. But our final goal was to show that, in fact, this alpha T, so it says that there is a unique one parameter star automorphism group, and that unique group is actually the modular automorphism group. So it's, in a sense, what you have to show is the following. This holds for all A in R. So I'm going to rewrite it in this manner. So this is what we want to show. Of course, if you are able to prove that UT is delta to the IT, you would be done. That is already good enough to show that this alpha TA is the modular automorphism group. And that's what we set out to do. And here we use Stone's theorem to say that there is some possibly unbounded self-adjoint operator H, so that this holds. So effectively, this is what you want to show. Like maybe even something weaker could do it, but turns out like such a strong fact holds. So really, the whole strategy of our proof was boiled down to proving the following. What we want to show is that, in fact, this operator delta is equal to e to the h. So delta was, remember, was from the polar decomposition of the map S. You had this J, which was an antilinear isometry, and then you have this positive part was delta. So if you can show delta equals e to the h, where h is the corresponding thing for u, then you would be done. So this would finish the proof. So to that effect, what we had done was built up certain operators. So given K in the family F, so K, and just to remind you, F was the family where, what was the yeah, so it was all continuous functions. So F consisted of continuous functions with compact support. So maybe I should just write CC of R. And you had this additional condition that this integral of the inverse Fourier transform is finite. Dt is finite. And the inverse Fourier transform was defined for every complex numbers, g hat of z was defined as 1 over 2 pi integral of e to the minus I lambda z and g lambda d lambda. over R. Yeah. So, integrating over lines. So if you fix an S and integrate over this line, then this one-dimensional integral is actually finite. So this is true for all S. Okay, so that was the assumption on the family F. So it consisted of such functions, and that is a non-empty family. We'll see very soon. But if we chose K in the inverse Fourier transform of that, so things of the form G hat. So G hat, this integral is finite, so it's like an L1 function on these lines. And also, of course, by the Riemann-Lebesgue lemma, you have that this is also continuous and decaying at infinity, hence it is bounded on these lines. So of course, on strips also, this inverse Fourier transform will be bounded. So K is such a function. So it is integrable and it is bounded and so on. And using this fact, we had exhibited that integral R kt ft dt is equal to integral R kt plus I ft plus I dt. So by looking at this strip, so this was the strip or the real line, and this was where the imaginary part is equal to I, and we had done a contour integral and estimated these and sent as R goes to infinity. That means this width of the strip goes to, the length of the strip goes to infinity. Then you would have these outlier terms will vanish. So hence you'll have this equality. And for ft, so we had this assumption that it be continuous and bounded. So that was all the assumption that we had. And if we chose ft to be alpha ta b uu, and naturally we had then f of t plus I, we can choose as b alpha t a u u, and this is the case of interest for us. So let's just quickly revisit like the operator ak that we had. So how was ak defined? So anytime you have a k like this, we had defined an operator in R. If you remember, that was an operator in R such that akx dot y is equal to integral of kt utxy dt. So integral over R, or you can just write in short, where it is understood that for all vectors x and y in H, you have this equality. In short, you can write, given a k, you are defining it in this manner, kt ut dt. In other words, you are taking some sort of Fourier transform. If you're thinking of this as e to the iht, which we know exists like from Stone's theorem. So this is like taking some sort of Fourier transform of this function kt. Yeah. So ak, so ak of u is nothing but k hat of h au. Okay. So once we prove this result, that integral kt ft dt is integral kt plus I ft plus I, then what we had is the following fact. So integral R kt alpha ta bu dot u dt is equal to integral R kt plus I, and here you have b alpha ta. Or in other words, I can write this as like I move the b here. B is a bounded operator in R. In fact, this is the case. And so what was the conclusion from here? Right. So so if you think of this as some so let's call this, I think I used a different notation. Let me stick to that. It just makes my life simpler. So let's say this is LT and say this is LT plus I, and define KT to be this. Note that KT will still be in that F inverse hat if L is in that. So you have this. Now this is so this we were thinking of as AL b u dot u. Remember what was the definition of ALX dot y? So you had this one parameter alpha ta acting on the vector x and y. So here the vector is bu, and here the y vector is u. So you had this AL, and on this side what you have is AK U, B star U, right? Just reinterpreting like how we had defined these operators AL and AK. And we had also shown using the Hahn-Banach theorem that AK, AL in fact belong to R. Okay. So from here, what I want to conclude is that AKU is equal to delta ALU. So let's see how far we can get. So this is true if you have, so this expression is BU dot AL star U, which is same as AKU. So just the right-hand side, B star U. Now I have to apply an S somewhere. So let's see. So this is BU acting on F AKU. So F you can think of as S star, or essentially, so what I have done is applied S on both sides. So it's a conjugate linear map. So you get a BU here and you get a AK star U. Okay. So we still have to use the fact that AK of U equals K hat HAU. We are yet to use that. And what we know is ALU is equal to L hat H of AU, and there is a connection between K hat and L hat. If you have a translation, it becomes like multiplication by a certain amount. So what you do have is K hat of lambda is equal to L hat of lambda times e to the lambda. So K hat of lambda equals L hat. So we'll keep this in mind. But all we're trying to do is using all this Fourier transform business, we're trying to reinterpret the modular condition in a way where we'll be able to finish off this problem. So yeah, so we got this ALBUU equals AKU dot B star U. So from here, what I want to say is AKU is equal to delta ALU. So this is what I want to conclude. So is it clear? So you have this. You have AKU B star U. Then I apply S on both sides. Then I have right. Yeah. So this is exactly right. So I actually, I'm not sure why I wrote S star here, but this is exactly the same as SAK, right? All I'm applying S on both sides. So I have this. Now you notice that as I vary my B, this equality will still hold. So in particular, what I have noticed is that AL star U is equal to SAKU. So AL star U equals SAKU, which is equal to SALU. So simply, like if you look at this definition, S of ALU, since AL belongs to R, by very definition, you have this. Now AKU, if I multiply S star, I get this. So I have S star S, AL acting on U. I think I made a mistake somewhere. S star S. Then I want to say I get a delta squared out of it. So this is supposed to be delta ALU. I think there should have been an S star here. So maybe I was correct in the beginning, but what's going on now? So you have ALBUU So which means you have a BU AL star U from this side, and from this side, you still have this AKU B star U. Now, if I apply S, I see. J, you have to apply J, not S, right? Because J is that conjugate linear isometry. So my bad. So you have to apply J from for both sides. So you have J AK, J B star U, AKU, and we'll have to look at the definition of J and so and use the properties like J delta to the IT is equal to delta to the IT J and so on, like J delta inverse is equal to delta J. Those properties you have to use, and the eventual conclusion you'll reach is this is equal to BU of S star AKU. So I'll leave that as an exercise to you. And yeah, so now this will work out. So actually we need an S star here. Yeah. Okay. So once you have an S, so not an S star, but rather an S. I mean, I'm kind of working backwards. So here you have AL star U. You want it to be equal to SAKU. So you have SAKU, let's say, is AL star U is equal to SALU. Then if I multiply S, then I get something like AKU. So using S squared equals identity. So if I had an S star here, then I would get SS star ALU, right? But delta was S star S, right? So I get a delta inverse instead. But that is not what I was looking for. Yeah, so I think instead of wasting too much time on this, so the conclusion will be once you figure out what exactly should appear S or S star, the final answer is that you will get AKU equals delta ALU. So this you will call the reinterpretation of the modular condition. Of the modular condition. And then the conclusion that you reach is AK of U is equal to K hat H of AU. That was what we had observed anyway, like in the very just using definition of Fourier transform on the way AK was defined. So you can say AKU is equal to K hat H AU is a consequence of the way the modular, the way the operator AK was defined. And then you have this is delta AL of U. So this equality is what we just noted here. AKU is equal to delta ALU. So that's what we are writing here. Now, same thing you can talk about ALU, right? So that is nothing but L hat H of AU for the exactly same reason as why you have K hat H AU here. Now, remember what we had is since it's just a translate, like K and L are just translates of each other. When we take the Fourier transform, the translation kind of is like a modulation, right? It becomes multiplication by this amount, e to the lambda. So once we put that here, so L instead of L hat, you have e to the minus h, K hat h, AU. So summarizing all of this, what you have is K hat h AU is equal to delta e to the minus h, K hat h AU. So this is already suggesting something, right? It's suggesting that so as I run over all A in R, this is running over a dense subset of H. So you suspect that this must be some sort of identity. And that's really what you set out to prove, that delta is equal to E to the H. So for that, you just need a little bit of a technical tool. So what we have shown now is delta inverse. Let's move the delta here. So this is behaving like e to the minus h, k hat h, au. Now, if this were like identity, if k hat h were identity and you're running over all of it, then your proof would be done at this very moment. But we may not have identity, but we have approximations, right? What we can do. So all we have to do is choose gn of lambda to be the following function on the complex plane. So we'll draw a disk of radius n. So disk of radius n, and then you just linearly decrease to 0. On the boundary, the value is 0. So, so essentially, you can define it on a line and just rotate the whole thing. So effectively, in one dimension, the function, the graph kind of looks like this. So what is the value? It's equal to 1. Yeah. So at 0, gn of lambda is equal to 1. At n minus n, it is 0, and it is declining in a linear fashion. And once you have built this function on the real line, you just rotate it to get a function on the complex plane. And it turns out the inverse Fourier transform, which you can explicitly compute, is 1 minus cosine nz over n pi z square. This, by the way, is a continuous function with compact support. And all you need to note is that this belongs to my family F, simply because what you're getting is an L1 function. This is this is bounded, and this is bounded below by a z square. And you know that 1 over so is this right? So yeah, all you need to do is check at 0, but there is a removable sort of singularity at 0. So you'll be fine. It's still a continuous function near 0. And at infinity, anyway, this is an integrable function. So no issues there. So using this as your k, and you can know as n goes to infinity, gn actually increases to the identity function, right? The constant function 1. So this kind of starts behaving as that identity operator. So in a way, as you change your n's and you change your a's, so this fact was true for all k in this. So in fact, since I've taken k hat, I can think of this as being g, where g belongs to f. So you have this equality where you're talking about JHAU, you're varying A and varying G, still this equality will hold. Now, as you vary A over all things, then you'll get a dense subset. And as you vary G over all such functions, you can approach identity as closely as you can. So in fact, this put together is forming a dense subset. So these two things match up on a dense subset. So since we have not talked about unbounded operators yet, but roughly you can believe that you get something like delta equals e to the h, and that's exactly what we wanted to prove. So delta to the it is equal to e to the ith, which was ut, and hence alpha ta equals ut a ut star equals delta to the it a delta to the minus it. So in a way, this kind of closes a parenthesis in Tomita's main theorem. So what we've showed that if like anytime you have this faithful normal state, you have this GNS representation, and you have this natural map on this, on RU actually, from RU to RU, which sends AU to A star U. In the matrix case, all of this was like bounded operators and very well defined and so on. But in general, you have this, and then you decompose S as this, J delta to the half. And then this delta had this nice property that delta to the IT R delta to the minus IT. So here you had used Gardner's theorem, like to go from similarity to unitary similarity. So we had used that. So you have this one parameter automorphism groups. Then we showed that this particular automorphism group like has this modular condition relative to omega. And then we have completed, like we have gone the reverse way. We have shown that this is very uniquely associated with that. And the techniques use Fourier transforms. And one of the things, the reasons why we are talking about Stone's theorem is to, and also the representation theory of L1R, very like we didn't cover all details, but the idea was to show that anytime you have a one parameter automorphism group, you should think that there is a representation theory of R going on, or L1R going on, if you are looking at the algebra generated by these operators. So that's why it's very natural to expect that like in such a proof, Fourier transform should make an appearance. So that was what I was trying to convince you. Okay. So there are two things I really want to do at this moment. One is justify very carefully all these steps. For example, here I notice that if U is a cyclic and separating vector, this RU is a dense subset, but it may not be like the whole set. And hence this S is a densely defined operator. And in fact, it may not be bounded. So we'll now clarify all the details. Before that, we need to talk about the theory of unbounded operators. And also, we don't have an example. Like, for all we know, this could actually be a bounded operator, right? Although I can heuristically convince you that this need not be the case, because when I'm looking at AU and A star U, what's going on? Let's say U is like, you're looking at a matrix, and U is like, let's say E1, 0, 0, whatever. Then I'm looking at the first column here, and here I'm kind of looking like the first row of A. So this is like looking at first column of A. And this is like looking at, let's say, first row of A. So, I mean, and then for other vectors, you make the appropriate like unitary conjugation so that this becomes like a unit vector. But roughly what I'm trying to say is the norm of the first column of A need not have any connection with the norm of the second column of A, first row of, what am I saying? So the norm of the first column of A need not have any connection with the norm of the first row of A. For example, the first column of A could have very, very small norm, but I can adjust whatever like things. I mean, this is not a rigorous proof, but this is just to convince you that in general, you should expect this map, which sends AU to A star U, to be an unbounded thing. For matrices, somehow you have finite dimensionality, so you're able to figure out some sort of the fact that S is bounded, but the bound will be pretty bad. Like, it will be massive, like depending on what is the size of your, like if you are talking about n by n matrices, it will be a pretty bad bound here. So that's all. So we don't expect this to be an unbounded operator, but still we need an example. So that example, hopefully we'll see it next time. So an example where it will be very, very like using Fock spaces and so on. So we'll define Fock spaces, we'll define a certain state on it, and we'll talk about so all of what we have seen, we'll try to see in a very specific case, and there we'll see that this S will turn out to be an unbounded operator. So then we're not left wondering whether like we are making a fuss about like something which is not really necessary. Anyway, so here we pivot away to a more fundamental study of unbounded operators. And then we'll redo all the proofs. As promised, we'll redo all the proofs that we have done in proving Tomita's main theorem, but we'll be quicker now, because now that we have the intuition, we'll be much quicker this time. But we'll dot all the I's and cross all the T's. Okay. So we'll talk about some basic notions. So you have H, a Hilbert space. And let's say T is a map on a subset of H, although we'll denote it like this. So the domain of T will sometimes write it as dom T or sometimes dt. So this is called the domain of T. So T is a linear operator defined on a linear submanifold of H, or you could say a linear subspace of H. So it's a linear operator defined on a subspace of H. So this is kind of like you could say some abuse of notation is going on here. Really, T is not defined on all of H. So you just say that you have a Hilbert space, that's what you start with. Now you want to study operators on the Hilbert space, but sometimes certain operators may not be defined on the whole of the Hilbert space. So you want to talk about, okay, T is related to this H, but the domain of T is actually not the whole of H, but it is something contained in H. For example, you could have H is equal to L2 of R, so with the Lebesgue measure and so on. And maybe you want to talk about this very important operator called ddx, the differentiation operator. But of course, not all L2 functions can be differentiated. So maybe you want to restrict your attention to something like C infinity or maybe even C1. So C1, C infinity R sitting inside, or maybe I should say CC infinity R, because I want it to be square integrable. Now this is going to be dense in the L2 sense in L2R. So you have ddx is defined on a, so ddx, so there are different ddx. So I should be careful here. That's why actually unbounded operator theory is a very, very treacherous territory. So small mistakes can cause you great harm. So when I say ddx, there is no individual operator. If I say the operator, I have to specify its domain. And if the domain is different, the operator is assumed to be behaving very differently. So here, what I'm trying to say is it's a differential operator with the domain, let's say CC infinity R. Someone could talk about differential operator with domain CC1R. So those two are different operators because the domains have become very different. Okay, so this is the kind of context where we want to study it. So typically there is a trade-off, right? These are certain operators, this, and let's say the multiplier operator mx, meaning if you give me an L2 function or any function, then I want to multiply by this function. But really, since this is unbounded. If I have an L2 function, I multiply by x, even if it's has some decay properties, you can still have it as not L2 anymore. But still, if I again restrict to CC infinity R, then this multiplier, which sends f to x times f, or rather fx to x times fx, this is so with domain CC infinity. So these are the kind of operators that we might want to study, we might be interested. So it's kind of like a trade-off. So here the space is nice. It has nice topological properties, which we think we understand. All Hilbert space kind of looks like L2 of n, or like square summable sequences, depending on what cardinality you have for the orthonormal basis, and so on. So our space is nice, but somehow studying the operator becomes hard. So our space is nice, this operator is of interest, but studying it becomes hard. You can, of course, change your space. Instead of talking about L2R, I could talk about, let's say, Schwarz functions. Then ddx will become a homeomorphism. Schwarz functions will form a F space, and you have the homeomorphism. But then the space is not nice enough. So you have very little control over the topological properties of that space. But anyway, that's another direction of study. But here we are thinking of this space H as being of paramount importance, and this operator being of importance, and then we'll struggle through the theory. So that's the trade-off. Either you make your space nice and then have this operator behave very nicely on that space, but still have a poor understanding of the space. But in this case, the space is nicer. So both have their advantages and their disadvantages. So in this case, we are going to stick to this description that our space is the one we really, really care about. We don't want to get rid of the space. And now we have to struggle with the whole theory. Okay. So any arbitrary unbounded operator. So these operators, by the way, which are not necessarily defined on all of H, we'll call them unbounded operators. So such T, this pair, or dom T, dt. So these will be called an unbounded operator. All bounded operators will be considered unbounded. So unbounded means not necessarily bounded. Doesn't mean that it is not bounded. It means not necessarily bounded. So in that case, so for a bounded operator T, if T is bounded, then domain of T is all of H. So in that case, there's not much to be said. But of course, if we didn't have any condition on T, if we were looking at any arbitrary operators, then it would not be very interesting. There's no analysis going on. Maybe set theory is going on, maybe some algebra is going on, some like very basic linear algebra is going on, but no analysis is coming into the picture if you're looking at arbitrary operators. So we need certain conditions. So certain conditions on this operator T, which will help us exploit certain properties of bounded operators. So one such condition is of that being closed. So definition, T is said to be a closed operator. So take a careful look at this definition, because in our discussion in Tomita-Takesaki theory, the operators S that we had defined will turn out to be a closed operator. So a lot of this theory, all these definitions that we are, so it will not be a vacuous definition. In fact, already at the level of differentiation on the appropriate domain turns out to be a closed operator. So you have actually plenty of examples of closed operators, so nothing to worry there. But yeah, so closed operators have good properties. So what is a closed operator? If graph of T, which by definition is x comma T of x, where x belongs to domain of T, which by the way is a subset of, let's say, H direct sum K. Did I use a different K? Yes, I did. So now I have this map from a Hilbert space H to a Hilbert space K. So if I look at the graph of this operator, then x comma Tx is going to be a subset space of linear subspace of H direct sum K. Linearity is clear. So if this is closed in H direct sum K, so in a way, what you're trying to do is borrow some sort of continuity properties, and we know from closed graph theorem is that T is bounded if and only if graph of T is closed. So this is the closed graph theorem. So if you have a linear operator defined everywhere, so just using that as some sort of motivation, you say that, okay, I mean, I may not have T is bounded, but I'll just say, like, if the graph is closed, I'll call that a closed operator. And we hope that we'll be able to borrow a lot of properties from bounded operators. In fact, in a very, very definite sense, that turns out to be true. So I will not be proving this fact. Let me just state it, that every closed operator is of this form. every closed operator. In fact, the paper I shared today morning on operator ranges, and okay, maybe not just that paper, but yeah, but in general, you can figure out from the literature that this is true, that every closed operator is of the following form, so every closed operator, let's call it T, is of the form T equals PQ inverse. It's like saying, so where P is bounded and Q is a bounded quasi-invertible operator. So essentially think of it as a fraction. So it's like, so what is a quasi-invertible operator? So Q is a bounded operator is said to be quasi-invertible if it has, so Q is quasi-invertible means Q has trivial null space. So it is a one-to-one map and it has dense range. And we know that if I look at such a quasi-invertible operator, and if I look at graph of Q, so look at graph of Q, what is it? It's x comma qx, right? So that x belongs to all of h. It's just a bounded operator. X belongs to all of h. Now, if I restrict my attention to range of Q, then maybe I should call it a different thing. So Q inverse y comma y. So these two sets are actually identical. I'm just rewriting this. Whatever is in the range in Qx, I'm writing it as y. Then this is nothing but Q inverse of y. So this, if this is closed, since this is closed because Q is a bounded operator, this must be closed, right? This graph of Q inverse, this is nothing but graph of Q inverse, where the domain of Q inverse has been said to be equal to range of Q. So this is a dense subset, right? Because Q has dense range. So the domain of Q inverse, which is well defined simply because Q has trivial null space, so it's a one-to-one map. So I can define Q inverse on a dense subset of H. So this already we are getting an example of a closed operator. So inverses of quasi-invertibles. So example, inverse of a quasi-invertible operator is a closed operator. Of a quasi-invertible operator is a closed operator. It has closed graph, and it is, and we know that such examples exist. In fact, like one of the basic examples you see would involve, I guess, weighted shifts in some sense. No, not even weighted shifts. If you look at, let's say, P A E n equals lambda n E n. Let's say P is nice self-adjoint kind of thing where lambda n goes to 0 as n goes to infinity, and lambda n is not equal to 0. So for example, I could set it to be, let's say, 1/2, 1/3, and so on. Then this is a quasi-invertible operator, in fact. So P E and E n, let's say, is an orthonormal basis of H, and let's say, let's put lambda n equals 1 over n. So this will have trivial null space, and it will have dense range, because if you, because in fact, all the EIs are in the range, right? So of course, all the span of the EIs will be in the range. So if ENs is an orthonormal basis, this will have dense range, but it will not be invertible simply because you cannot put a bound on. So there is no lambda such that you can do something like this, right? For a unit vector, you cannot do something like this simply because P of En is equal to 1 over n En. So you cannot really invert this P. But if you are forced to invert this P on the range of P, then you'll get a closed operator. It will be an unbounded operator, but it will be a closed operator. So P inverse is a closed unbounded operator. So you can think of this, typically I like to think of this as, so when you're trying to do change of basis, at least for matrices, anytime I choose, let's say, some orthonormal basis V1, V2, Vn, not orthonormal, just any basis for that matter. Then, and then let's say I have W1, W2, Wn, and so on. Then correspondingly, there is a change of basis matrix, which will convert this V1, V2, Vn to W1, W2, Wn. But once you get to the infinite dimensional case, this is not always possible. So you may have a bunch of linearly independent vectors Vn who span closure. So span closure is equal to all of H. But that does not mean, and let's say you have another W1, W2, Wn, whose span closure is equal to H. So in a sense, these are like the basis for H, but that does not mean you have a P, a bounded P, so that PV1 equals W1, PV2. So that may not exist. We have already saw an example. Here you have E1, E2, En, you choose E1, E1 over 2, E3 over 3, and so on. So you already saw an example. So there exists no bounded, no bounded operator such that PV1 equals W1. So it need not be the case in general, PVN equals Wn. And this is one such example. So whenever we're trying to do change of basis and looking at the operators like PA, P inverse, and so on, that's what we're trying to do. We are not allowed to do it in general for B of H. But if we allow for these unbounded operators, we'll be able to make sense of change of basis in general. So that is where I would say this comes in very handy. It shows that closed operators are actually very familiar objects. Like we're not going to prove this theorem, and also it's not going to be used anywhere in the proof of Tomita's main theorem, but it's good to keep in mind that every closed operator is of this form. This is a bounded operator P, and you have inverse of a quasi-invertible thing, PQ inverse. So essentially, you're localizing with respect to this multiplicative set. So if you're algebraically minded, you may have seen, okay, you have these quasi-invertible operators. Products of quasi-invertibles will also be quasi-invertible. So essentially, you are trying to force inverses for this multiplicative set. And if you try to build that set, you will have...
You're saying this result is in the paper you mentioned, right?
You can use the results in the paper to prove this. There is another paper which I didn't mention in your in the email, which is about quotients of closed operators. It is from the 70s. I forget the author.
Okay.
Yeah, but anyway, maybe I'll share it. But this paper on operator ranges, maybe I will mention this result, because a priori what it looks...
In the previous case, the PAs and W are not optimal. They are just linearly independent.
Yeah, so the question is, in this example, it's not necessary that these are orthonormal bases. That's true, because if you have orthonormal bases, there is always a unitary, which you can do this. Yeah. So what I'm saying is, in general, we're talking about change of basis, not just change of orthonormal basis. If we are talking about change of orthonormal basis, then UA U star, that we are familiar with. You can implement that using bounded operators. But if you're just talking about change of basis, you cannot implement just using bounded operators. You need unbounded operators. So that was my point. So yeah. And coming back to this assertion, so why did I share that paper on operator ranges? Because it answers a very, very nice question, which is very natural when someone encounters unbounded operators, which is the following question. So you have H and you have V. So the question is, can any linear subspace of H be the domain of a closed operator? So are there any restrictions? If you have a Hilbert space H and I'm defining some closed operator in H, are there any restrictions on what the domain can be? So initially, at least, like so when I said it's surprisingly not found in many textbooks, actually, I think this will help you build quite a bit of intuition on what closed operators look like, but somehow most standard textbooks don't talk about what the possible domains could be and what a general closed linear operator looks like algebraically. So, but anyway, these are not really very hard results, but yeah, but for some reason they don't appear in most textbooks. So yeah, so the answer is, of course, the way it is phrased, the question is phrased, the answer is no. Not every linear subspace can appear, but which linear subspace can appear? So V is the domain of a, so the following are equivalent, is the domain of a closed operator if and only if V is the range of a bounded operator. And in fact, the expression that I wrote PQ inverse, the domain is actually the range of Q. So this has domain range of Q. And then, of course, range will lie somewhere, will be some subset of H. So these two are in fact equivalent. And here, actually, I want to say that the domain need not be a dense subset. So here I'm saying that this is actually a densely defined closed operator. So I should actually add something. Every densely defined, my bad. So every densely defined closed operator But if you're allowed something called the Moore-Penrose inverse, which you can do for any bounded operator, the Moore-Penrose inverse sort of, if you're allowed to do that, then I can write it as PQ dagger. So then I can remove this densely defined and say every closed operator is of this form. Okay. So yeah, so we put in this closed graph condition so that we'll be able to extract something out of the unbounded operators. So what we see from these theorems is, in fact, these closed operators are intimately tied with bounded operators. And also you do have examples. You do have examples like of interest like ddx, or if you're doing change of basis and so on. So having said that, we'll move on to a few other discussions about unbounded operators, and our focus will always be on closed operators. Okay. So yet another definition. So let's say you have T and domain of T or D of T is dense in H. Let Y, so we're going to define the adjoint of T in this case, adjoint of this unbounded operator. Let Y be an element of H. Actually, I should say element of K. Let Y be an element of K. So because the map T is from H to K, so the T star will be actually a map from K to H. So let Y be this such that the map X to Tx dot Y. By the way, in order to make sense of the right-hand side, this better be in the domain of T. So this is a dense subset, and on this dense subset, I'm defining this functional. This is bounded. So again, repeating, let Y be an element of K such that this map, which we have defined on the domain of T, it's a linear map and it's a map to the complex numbers. So this is bounded. Then, of course, you can extend this map to the whole of H. And then by the Riesz representation theorem, you'll have that this is equal to X dot Z for all X, because forget about this T of X. This is a linear map in X. Hence, you will have some Z so that this is X dot Z. So this Z will also be unique. So you define Z as T star Y, or rather you define T star of Y as this and say that Y belongs to domain of T star. So of course, in the bounded operator case, this is always a bounded functional, so you don't have to say it in this sort of indirect way. So because I'm saying this is very slippery territory, we have to be very careful how we define things. I'm going to repeat this. So what I'm saying is, if Y is in K such that this is bounded, then Y belongs to domain of T star, and T star of Y is defined as this Z. So T star of Y is what we want to define. So maybe I should write it this way. So T star of Y is defined to be equal to Z. And then you can check linearity and all that. So this is how adjoint of an operator is defined. And it is not necessarily true that T star should have non-trivial domain. Of course, 0 belongs to domain of T star. 0 belongs to domain of T star. But like there's no, like a priori, you don't have good reason why you should have more things. But under certain conditions, you can be sure that the adjoint of this operator T will have a much bigger set. So here's a quick remark, is that if T is densely defined, meaning the domain of T is a dense subset, if T is densely defined, then T star is a closed linear operator. T need not be closed, it just has to be densely defined, then T star will be a closed linear operator. And I say again that there is no reason to expect that the domain of T star is huge. T star could be a very, very trivial sort of operator. But whatever it is, it has to be closed. And this follows from the following fact. We have to reinterpret the closed graph theorem in the following manner. So graph being closed, what does it mean? It means if I have a sequence in the graph, so what do the sequence looks like? Xn T Xn goes to xy. If this goes to xy, this implies xy belongs to graph of T, right? That's what it means for the graph to be closed. Now, in other words, what does it mean? It says that if xn goes to x and txn goes to y, then tx is equal to y. So that's exactly what closed graph being closed means. The graph being closed means if xn goes to x in H, txn goes to y in K, then t of x must be equal to y. Yeah, right. Yeah, and of course I should say xn belongs to domain of T and so on. Yeah, and x also should be in domain of T. Right. Otherwise, this definition will not make sense because we are all staying within graph of T, and all the first coordinates of the graph of T consist of elements in the domain of T. Right. So, so that's just interpreting what the condition of the graph being closed means. So here, if I have to show T star is a closed linear operator, that's exactly what I have to do. And by the way, so once I have this, xn minus x is 0. So equivalently, I can say that if xn belonging to dt goes to 0 and txn goes to y, then y equals 0. So this is the standard way it is going to be used, this condition of being closed. This is the standard way to prove it. So again, repeating, if xn goes to 0 and txn goes to y, the only choice you have for y is 0. If you prove that, then you have proven that T is closed. So here what we want to show is T star is a closed linear operator. So let's assume Vn belongs to domain of T star and Vn goes to 0 and T star Vn goes to 0. So these are all the assumptions that we have. So what we, T star Vn goes to y. So what we want to show is that this y must be equal to 0. Then that will prove to us that T star is a closed linear operator. Okay. Now, if Vn goes to 0, then for any vector x, I have the following, right? This goes to 0. So I'll choose x to be in the domain of T. So if I choose x in the domain of T, I have x dot Vn goes to 0. Now, Tx Vn also goes to 0. Tx is just a fixed vector. X is in the domain. So I'm just using the fact that Vn goes to 0. So now, since Vn is in domain of T star, then I can actually move this T to the other side. So what I conclude is, in fact, for every x in the domain of T, you have T star of Vn goes to 0 for all x in domain of T. But that, here, what have we assumed? We have assumed T star Vn goes to y. So for that, this also goes to x dot y. So what we conclude from here is that x dot y is in fact is equal to 0 for all x in domain of T. Now, how do I compute the proof? Then I just use this condition that T is densely defined. So on a dense set of x, you have this. So this implies y must actually be equal to 0. And that proves that the graph of T star is actually closed. All right. So whenever T is densely defined, T star is a closed linear operator. Again, T star need not be non-trivial. It could be something very uninteresting, just that it is closed. Okay, so we'll prove certain conditions. Like, for example, if T is closed and densely defined, we'll actually conclude that T star will also be closed and densely defined. So for those sorts of operators, T star, all these operations will give you very, very nice and non-trivial operators. So in order to show such theorems, we need a small lemma. So in this lemma, I need a definition. First, let me define this unitary operator, which is just like a shuffling with a minus sign. It's like a sort of a reflection. So V, it sends, so phi comma psi. So there is a vector phi psi here. What I will do is reflect, like if it were like, so reflect about this line, we'll do x, y, y, x. I guess you reflect about this line. If you reflect something about this line, you get something like minus yx, right? If you have xy, you get minus yx. So something like that. So it's easy to see that it's a unitary operator. So V is unitary. So the lemma is if domain of T is dense, remember that is exactly the condition that we wrote here, then graph of T star is equal to V applied to graph of T perp. So graph of T is a closed subspace of H cross H. So I'm applying this unitary operator and I'm ending up with another closed subspace. Here I'm looking at the perp. So what we have is, it's just again manipulation of inner products. But it will help us prove a couple of theorems quite easily. So why is that? So let's go from one direction to the other. So if something belongs to, if phi psi belongs to graph of T star, what does that mean? So this means this psi must be T star phi, right? By definition, anything that belongs to the graph is of this form x comma whatever operator times x, right? So here you're in the graph of t star. So the psi is t star phi. So this is true if and only if t eta phi is equal to eta psi for all eta belonging to domain of T. I mean that I'm just using the definition of phi being in the domain of T star, right? Phi is in the domain of T star, then you have this condition. Now I'm going to subtract this, so you have a minus eta psi, and I'm going to use the inner product in h dot h cross h. So phi psi here and minus t eta here is equal to 0 for all eta in domain of T. So this is just writing out the inner product in h cross x. So you have a phi dot minus t eta. So I'm moving this here, then I plus psi dot eta. So it's just a restatement of this fact. Now, what can you say about this? This is, remember, what is the definition of V? V of phi psi, it just flips them and puts a minus sign on the top. So this is nothing but V of eta t eta by definition. And this is nothing but things in the graph of T, right? This vector belongs to graph of T. So here what I have is elements of V of graph of T. Here I have a generic element of G of T star. So what I've concluded is that they're orthogonal to each other. So that's all, just manipulating inner products. So phi psi belongs to V of GT part. Okay. So here comes an important theorem. And there will be 3 theorems that I want you to be 3 or maybe 4, I should say. I mean, maybe you can observe this theorem in the next theorem, but anyway, so that 3 theorems, let's say, that we have to be very, very comfortable with, because we'll be continuously using this in proving Tomita's main theorem, rigorously. So here, maybe theorem part A. Let's call this part A of this theorem. If domain of T is dense, then we have the following. Then 1, T star is closed. We already proved this, but I'm going to just state it here also. Then T is pre-closed or closable. By the way, I have not defined this. But it is what you would expect from these terms, like closable. Meaning you can actually, even if the graph is not closed, if you close up the graph, you get a graph. You don't get like multi-valued functions out of it. So if and only if domain of T star is dense. So I think this is the right time to define what pre-closed means. Pre-closed just means that if you give me any operator at all, I can talk about the graph of T. The graph of T need not be closed, and I can always close it up. But graph of T closer may become multi-valued, may become. So graph of, since I'm using T here, let me use another symbol here. So this may become multi-valued. What does that mean? That you may have an X where you have a value Y. So XY belongs to graph of S closer. And you also have X of Z belongs to graph of S closer, and Y is not equal to Z. If it is not multi-valued, then what you can do is extend this definition. You can just assign whatever value Y you have, you can call that S of X. So that's called an extension of S. So yeah. So anytime like if this is not multi-valued, if GS closer is not multi-valued, then the corresponding function operator that you get will call be an extension of. So S, this will be an extension of S. And if the extension, or you could say the smallest extension to this closed subspace is closed, then it is said to be pre-closed. Let me repeat it if it's not clear. So first you start with T, then you look at its graph, which may or may not be closed in H cross K. Then what you do is close up that graph. If that whatever closed subspace you get is kind of multi-valued, like corresponding to a single X, you have multiple values, then you are not able to assign X to a fixed Y. In that case, you would say that T is not extendable to this bigger domain. But if you are able to extend, and that extension is a closed operator, which it will be, simply because the graph is closed. So then in that case, you will call T to be pre-closed. So here we are saying T is pre-closed or closable if and only if domain of T star is dense. Then number 3, T is closable if T is closable. I mean, for example, closed operators are trivially closable. You don't have to even extend anything. So if T is closable, then T bar star, so T bar is that extension, is equal to T star. That means if T is closable, you close it up. That is what you call by T bar. So this is called the closure of T. Then if you take its adjoint, it is the same as adjoint of T. And then I'll include 4 and 5. If T is, so maybe 4 and 5, I will call it theorem part B, because here what I'm doing is assuming domain of T is dense. For this part, I don't need to assume. I mean, you can always add that assumption, but it is not, that assumption is not necessary. So here, let me just say if T is closed, then 1 T star T plus I has range H, all of the Hilbert space, no density, nothing, all of the Hilbert space. If T is closed, then T star T plus I has range H. Remember, oh, by the way, I have not defined what T star T means, but you can, whatever you guess will be the correct answer. It's exactly the operator which makes sense. No, you can always define T star, even if T is not densely defined, right? T star.
But that rate may not be.
Oh, yes, that's right. Okay, so we do need that assumption that T is densely defined. Okay, so okay, so maybe let me include this as a 4 and a 5 then. So T is closed and densely defined. Yeah. So what you are saying is that if T is not densely defined, then T star that may not be unique Z, so it may not be properly defined. Yeah, that's true. You can always choose something in the path. You can add that. Yeah, right. So you do need closed and densely defined. So in that case, I should only have defined T star for densely defined operators, not just arbitrary operators, right?
Yeah.
Okay. So yeah, going back to the definition. Anyway, like in our case, we'll be mostly dealing with densely defined operators, so it doesn't make a difference. But here, maybe when we defined T star, so as Indrajit is pointing out, is that if domain of T is not dense, then the Z that you get may not be unique. So here it may not be possible to define properly what T star Y is. So only for densely defined operators, T star would make sense. So let's stick to that convention that we'll only talk about T star in the setting of densely defined operators. Okay. So here I have introduced two things. First of all, I have multiplied two operators. I have a T star and I have a T. So I have multiplied. So first I have to make sense of what multiplication of unbounded operators is. And then I have used the term core. So if I have two operators A, B, the domain of A, B is defined exactly how you expect. It's all those X in H such that X belongs to domain of B. Otherwise, I can not even talk about B of X, right? First of all, it has to belong to domain of B, and B of X belongs to domain of A. So it's exactly how you'd expect it to be defined, like A, B of X. So first of all, BX has to make sense. Then after you define BX, then BX, A of B of BX has to make sense. So X belongs to domain of B and B of X belongs to domain of A. So that's how domain of AB is defined. And core just means that if you give me some operator T, unbounded operator T, and then you have a corresponding domain of T, then a core for T is a subspace of domain of T. So let's call this V. This is core for T. If the graph of T restriction to V closure is the same as graph of T closure. So in a way, it contains most of the information that you want to get for T. So even if you're restricting your attention to a smaller set, you will be able to recover the whole thing just by taking closures in the graph. So I hope this definition is clear. So then V is the core. And it may look like a technical definition, but maybe just to not spook you, I should give you this hint, is that if you're looking at unbounded self-adjoint operators, you'll have a spectral theorem which looks like this. Typically, you'll have a minus norm of A to norm of A. So here you have an unbounded self-adjoint operator, you'll have something like this. Then you'll talk about a core. The core will consist of certain bounded things. The core will be all vectors. So union of this. So union from n going to 1 to infinity. So this will be all familiar looking vectors. So you're building these up using bounded operators. So this will form a core for A. And A will be closed and densely defined and all that. So you will have this self-adjoint operator. So that's why the definition of a core becomes important, because you want to extract a nice set. For example, when you look at ddx, I said we can define it on CC infinity. But really, that does not make it a closed operator. It will become closable, but it's not a closed operator. So in order to have it a closed operator, the domain has to be all those absolutely continuous functions which are differentiable almost everywhere, and the derivative is also L2 and so on. That will be actually, if you close ddx up, that will be the domain. But really, that is hard to work with, right? You don't want to work with all these technical conditions saying absolutely continuous and the derivative is L2 and all this. But this CC infinity, I believe, will form a core. I'm not 100% sure. I'll have to look back. I don't want to make a wrong statement, especially when dealing with unbounded operators. But generally, what you want to do is extract a core, meaning you want all these nice vectors, so nice functions in this setting. You want the nice functions, but at the same time, you will be able to approximate everything in the domain using those nice functions. And like, for example, I could have chosen nice functions which are let's say all CC infinity functions which are vanishing from -1 to 1. So that is also a set of nice functions where derivatives can be defined, but that's not a core, because there are many like functions which you cannot hit using those functions. So CC infinity of R, let's say, vanishing on -1 to 1, this is not a core. So core is like, it's like a dense thing. It is capturing the key properties of this operator ddx. So that's the way you should think of it. So yeah. So I have this 1, 2, 3, 4, 5. And this I'm claiming is that, first of all, it's not very clear that whether domain of T star T is even non-trivial, right? Like you never know. Like it could be possible that T of X is never in the domain of T star. So in that case, it will be 0. But what it is saying is, in fact, there is a large enough domain of T star T. And in fact, it is large enough such that when you apply that to the domain operators, the end result is you get everything in H. You recover everything in H. Okay. So this is one key theorem. Since I have 20 minutes left, I'll defer the proof to the end. So, and maybe we can continue next time. But I want to state first the 3 key theorems I want to look at. The next thing is, if domain of T, so if T is closed and densely defined, then T star T plus I is 1 to 1 with range H. So 1 to 1, so it is injective, range H, it is surjective and positive, meaning you take any vector X and dot with X. So X in the domain, then the answer is always positive. Yeah, and has positive inverse of bound not exceeding 1. And 2 is T star T star is equal to T star T, which is another way of saying T star T is self-adjoint. Here you again have to be careful, is that you cannot just manipulate saying that, okay, I know AB star is B star A star and T star star is equal to T. So all of those luxuries are not available to us, because you have to first, this equality always contains this following information, that domain of T star T is equal to domain of T star T. So if I'm saying that two unbounded operators are equal, A equals B, hidden in this fact is the fact that, hidden in this statement is the fact that domain of A is actually equal to domain of B. So first, typically what you have to do is first prove the domains are equal and then show that they match up, they agree on the domain. So T star T is always going to be self-adjoint. And another part of this theorem is that if T is self-adjoint, then T plus minus I has trivial null space, which means it is one-to-one. And range H with bounded inverse having norm not exceeding 1. Having norm not exceeding 1. Okay. So why so? So again, like before trying to prove these theorems, let's get an intuition about these facts. So here I'm saying, okay, let's pretend that T star T is some self-adjoint operators, and maybe it is unbounded. So typically what will happen is that the spectrum could be an unbounded subset of the real line. So for bounded self-adjoint, you have a bounded subset of the real line. For unbounded, it could be the case, this happens. And for positive things, it will be on this side. So this is 0, it is on this side. Now, if I translate this by 1, the spectrum of whatever is coming will start at 1, right? If I'm looking at T star T, whatever spectrum means, like, again, I'm being very, very loose. We'll prove it specifically. I want you to get the intuition. Now, if I invert this, it's going to end up in here. It may not hit 0, but inverse of this will actually turn out to be bounded operators, which norm not exceeding 1. So that is the general idea. And same goes for T plus minus I times identity. Now, if I have a self-adjoint operator, not necessarily positive, now if I translate it by an amount of I, it's going to end up here. So this is I. So this was the real line. Now, T plus minus I kind of has spectrum in here. Now, if I invert this, invert in the complex number sense, if I invert this inversion, maybe from geometry and all this, if I have a line which is not passing through the origin, if I invert it, it will turn out to be some sort of circle, right? So it will be inside actually this circle. So that's why you also have this. It will have trivial null. These all need a proof, but I'm trying to intuitively tell you that if you are thinking of a spectral theorem, unbounded spectral theorem, you expect that these to have bounded inverse with norm not exceeding 1, because you have translated by I in this direction and in this direction, and whenever I take 1 over this element, you can easily check that it will always lie inside this unit disk. Okay. So this was the key theorem 2. Then another key theorem that we care about is the spectral theorem for unbounded operators. For unbounded self-adjoint operators, let's say. So here also we have to little bit build our intuition. So let A be possibly unbounded self-adjoint operator on Hilbert space H. Self-adjoint operator on H. And let this script A be the abelian von Neumann algebra generated by A plus I inverse A minus this inverse. Now we know that, like from the previous theorem, that these are two bounded operators. So in a way, we have a good control over bounded operators. So in order to study unbounded operators, first we want to do a transformation, which will convert it into a bounded operator. Then we use whatever theorem, then transform back. So here what will happen is, anyway, these two commute, A plus I times identity and A minus I times identity commute, simply because, and this, by the way, is the star of this. This will turn out to be the star of this, because this is self-adjoint. So then, since these two commute, whatever one and they're star closed, so what they're normal operators, in fact. then whatever one-Neumann algebra they will generate will be abelian. And even in the general spectral theorem case for unbounded normal operators, self-adjoint operators, the way you prove is essentially you build the smallest one-Neumann algebra generated by it. Since it is a normal operator, it will be an abelian one-Neumann algebra. And in fact, all the spectral projections will be in that abelian one-Neumann algebra. So that is like the smallest algebra you should be talking about. You should not talk about the smallest abelian C-star algebra generated by some operator, by this normal operator, because it will not contain the spectral projections. But once you get to the one-Neumann algebra level, it will start containing it. And partly it is because of very nice order theoretic properties that one-Neumann algebra have. For example, monotone sigma completeness, meaning if an is an increasing sequence bounded above by, let's say, some self-adjoint operator A, then in the strong operator topology, an converges. So using these properties, what you can show is every abelian one-Neumann algebra kind of looks like C of X. First of all, it's a C-star algebra. So it does look like C of X for some compact Hausdorff space X compact Hausdorff. But because of this order theoretic property, what you get is X is what is known as extremely disconnected. And this disconnectedness allows for indicator functions to be continuous functions, right? Otherwise, if there is a lot of connectedness, then indicator functions will not be continuous because they will be splitting up things. Like wherever it takes value 1 is one component, wherever it is value 0 is another component. So if you want enough indicator functions in C of X, X better be what is known as extremely disconnected. Meaning, so if you have an open set, so closure of open set is open. I hope that's the right. Yeah, so closure of open set is open. So that is the definition. So you have a compact Hausdorff space where the closure of open set is open, then it is said to be extremely disconnected. So you have such properties. And in fact, one topological proof of the theorem you can find in Caddy-Sundringos chapter 5. One of, I guess, my favorite proof, because although measure theory is hiding there, but you can just using topological means, you can prove this by noting that this abelian one-Neumann algebra generated by this normal operator is like C of X, where X is compact Hausdorff space, where you have this. And then you look at the appropriate indicator functions, which will give you the resolution of the identity. Okay. But here what happens? Here we are dealing with unbounded operators. So what will happen in this case? And by the way, again, like one can show that this can be thought of, the connection with measure theory will happen in this way. You have a locally compact Hausdorff space and you have a radon measure on that, and you're looking at L infinity. So it's not the same X. Maybe I'll write like X prime or something. It's a different sort of X prime. So here X prime can be nice. Here we're saying X is very, very weird. It is extremely disconnected and so on. But here I can choose, for example, 0, 1, L infinity 0, 1 mu, where mu is maybe the Lebesgue measure and so on. Now, in order to accommodate these, so if I look at these abelian one-Neumann algebra generated by this, I'll get something like this, right? L infinity X prime mu. So then what does A look like? A, of course, does not belong here. A is unbounded. A, of course, does not belong here. A, in fact, belongs to L0 X prime mu, meaning it's a measurable function.
Here, I have one doubt. Like, what is the advantage we are seeing it as C of X, where X is extremely disconnected, over this, seeing it as L infinity of X prime?
So proving this, first of all, I would say is much harder. Like you have to okay. One advantage makes it clear is that the measure in the theory of one-Neumann algebras, the measure does not really matter. It's only the measure class that matters, right? Because you can always draw an isomorphism using the Radon-Nikodym derivative. So as long as your sigma algebra is the same and the ideal of null sets is the same, the L infinity will be isomorphic, right? So this, first of all, makes it very clear that, by the way, the measure 0 sets will correspond to what are known as negligible sets here. So that also you can check in, like, I think towards the end of chapter 5 in Caddy-Sundringos. So the advantage I would say is that it makes it very, very clear at the outset that it's not really the measure that matters. And the thing is, the proof is much quicker, because once you have this order theoretic property, which you can like prove, maybe I shouldn't say elementary, but like elementary one-Neumann algebra theory. Then once you have this order theory, and from Gelfand-Neumann theory, you have this description, you immediately conclude that X is extremely disconnected. Then when you talk about level sets, so any element in A is like a function, right? Every element in A is like a function in Cx. Now, if I want to do a spectral resolution, effectively, I'm looking at level sets in X, like E lambda. So those are indicator functions corresponding to, I'll have to be careful here, but X belongs to X such that, let's say, Fx is less than lambda or something like that. Either it is less than or less than equal to maybe. So I have to be a bit careful here. So you get a closed set out of it. Now, these are my resolution of identity. So then the proof actually becomes very, very quick. And it is complete. There is no gaps in the proof. But once you start doing measure theory, you have to be very, very careful so as to not introduce any gaps in your proof. So that's why I like this proof. But of course, I'm not saying that measure theory is not important. Of course, we do care to distinguish between Gaussian measure and Lebesgue measure, although the answers as a one-dimensional algebra you may get is the same. But yeah, it depends on what question you're trying to answer. And as you pointed out, in fact, this description becomes much more useful when you're talking about unbounded operators, because here, then you'll have to talk about essential functions. Because you'll have to talk about functions which are continuous functions which are not defined on all points of X, so outside of a negligible set. So it becomes a little bit more work. But in this description, it becomes very clear what the unbounded operators correspond to. So the unbounded operators essentially correspond to measurable functions in X prime. And all measurable functions, let's say I have 0, 1 here, any measure, it could be unbounded like this. You can cut it off at bounded parts. So you can choose n and minus n, and then you'll find an element of L infinity, right? So in a certain sense, and as you increase your cutoff, there is a certain sense in which these cutoffs will tend. So you have chi of, let's say, or rather, chi of f inverse minus nn. Let's say I'm looking at this f times indicator function of this, which means whenever the value is exceeding n or minus n on whichever direction, I'm just setting it to equal to 0. So this actually tends to f in topology of local convergence in measure. So there is an appropriate sense in which it happens. But at this level, already you're able to talk about these spectral E lambdas, these E lambdas. So then you have to find the appropriate sense in which these functions tend to f. It will definitely happen pointwise, but a little bit more than that. So, so the picture that you should have in mind is this, that even if you have an unbounded self-adjoint operator, you can generate an algebra out of it. And that algebra and star operation and everything, anyway, it's a self-adjoint, it's star closed and so on. It will actually look like something like L0x mu. But the proof of this, the rigorous proof of this, will have to go through this path. You first generate A, which will look like L infinity. Then you show that this A is actually an element of L0. So the actual proof will go via L infinity. But the intuition, you can say that, okay, I start with this, and this is just restriction. Like this is a much bigger set than L infinity. Okay. So yeah, and in fact, the term that is used, this is something we may see later. A is affiliated with this abelian one-dimensional algebra A. This is the term that we use. And in fact, you can talk about affiliation of an operator with respect to any one-dimensional algebra. But when you talk about finite one-dimensional algebras, the affiliated operators actually have a very nice structure. They form a star algebra, in fact, a topological star algebra. But otherwise, they may not have a good structure. But all of this is hidden in this proof. So these are the main theorems that I was talking about. Polar decomposition is yet another theorem, because you remember when we were talking about S, we did a polar decomposition, J delta to the half, right? So maybe I should mention this. Okay, I don't have time to do any proofs, so maybe we'll start doing the proofs of this, at least the first two theorems, because I don't think like if we start doing rigorous proofs of this theorem, spectral theorem for unbounded self-adjoint operators, it will take maybe half of this semester. We don't want that. So I hope you can believe like how the strategy will work once you get to this level of L infinity x mu and then try to go back by an inverse transform to L naught. But at least theorem 1 and 2 will rigorously prove, very, very carefully prove all of this. Okay, so the last theorem I want to just state is polar decomposition. We just say is that if you have any closed operator, closed densely defined operator, closed densely defined operator on H, then from H to K, let's even go more general, from H to K, then there is a partial isometry from range of T star T to the half closer to range of T closer. So this is the partial isometry, and on the complement, it is actually, So it's an isometry on here, and on the complement it is 0, such that t is equal to v of t star t to the half. And the proof of this uniqueness, I mean, anyway, we are not really that bothered with that, but the proof is identical to what you would do for unbounded operators. So what do you do for identical to the case of bounded operators? So there, what you do is you look at this expression, then you notice it is tx, then you see it is t star t xx. Then you notice that this is a positive thing, it has a positive square root. So then I can write it as t star to the half x, t star t to the half x. Hence, this is nothing but norm of t star t to the half x whole squared. So now if I look at this map, which will send t star t to the half x equals tx, this is an isometry on the range of this already, right? Onto the range of this, or into the range of this. But then, since this is an isometry, I can always extend to the closure and so on, right? This is literally how you define the partial isometry. Now, if I want to mimic the proof, what do I need to do? The modification I need to do is x belongs to domain of t. Then here also I'm using that x belongs to domain of t star t to the half. That is also a theorem. I think I stated it here. Domain of t star t contains a core for t. So in fact, instead, maybe I should say x belongs to domain of t star t to the half. So because all I need is to do this on a dense subset, right? If I do it on a core, that is already good enough. So if I choose here by that theorem that I just mentioned, so stare at it for a bit. So here I said domain of t star t contains a core for t. So if I prove things for x belonging to here, it is as good as proving things for all x belonging to domain of t. So that's what I start with. And you may see a square root here, but once you understand the spectral theorem, it will be clear to you that that you have a core, that en minus e to the minus n, that is still a core for even the square root, because then you are talking about square root this, right? So this thing is still a core for the square root. So maybe you should talk about x belonging to domain of t star t to the half, and so those exact things we'll revisit next time. But my point is, if I choose x in the right domain, which is the dense subset of H, I have this equality, tx squared. So then all I have to do is define it in V in this manner. And then V will turn out to be a partial isometry, and you will have V is equal to, T is equal to V, T star T to the half. And this closed, densely defined, all of this is needed to notice that T star T is actually a self-adjoint operator. So that's why we needed these conditions. In fact, one can go a little bit more and conclude that V is in the von Neumann algebra kind of generated by this T, and this is affiliated, like if you started with T being a closed densely defined operator affiliated with the von Neumann algebra R, then this V will belong to R, and so on. But anyway, as of now, we don't need those extra things. So we're going very minimalistic in our approach. All right, any questions? This is where I would like to stop today. Any questions? Okay, anyway, you can always email me, or we can start talking about it next time. I'll post the previous video and this video. I always need to edit because sometimes there's some issues with the technology and so on. So I'll do that. And next time what we'll do is prove the first two main theorems, and again repeat the heuristic about the spectral theorem for, in fact, unbounded normal operators. The same argument we'll go through. And talk about polar decomposition, and see the, if time permits, also see the example that I mentioned. Example using the Fock space and certain operators on the Fock space and a certain state, where we'll see that in fact the operator S that we'll define will be unbounded. So it's an important example where you'll see that S is unbounded. So we need all this machinery. It's not vacuous. All right. So see you next week.